Hi everyone, today I'll be presenting my work on physical layer aware and slicing under the guidance of my advisor, Professor Nilesh B. Mehta. So basically, what is slicing? So in 5G, there is a rise in demand for different various of services like URLLC, MMPG, EMBP with different kinds of requirements. But the thing is that in order to meet these requirements, it is not easy to create different multiple physical networks. So what in 5G we are doing is that we are dividing logically this physical network into multiple independent networks, which is called as a slice. So here, every network operator, mobile network operator, has their own slices, and the MVNO request for admitting their slice on infrastructure providers' resources. So the infrastructure provider base stations then can decide whether to accept these slices or not, and if they are accepted, how many resources they should be allocating. And how many resources that they are allocating is defined as a slicing profile. Uh, and then what is the RAN slicing enforcement problem? So basically, when you have multiple base stations and multiple resources and multiple slicing profiles to meet, how will you allocate resources such that the total number of the outputs that every user receives, whether it be cell edge user or web cell center user, what is the total rate that total rate that they will users will be getting, and how will you maximize something like that? So here you can see that the user two is being served by both base station one and base station two since it's a cell edge user, but one of them is the signal and the other one is interference, due to which SINR is very low compared to base station one serving the UE1. So it is necessary that we implement resource allocation such that there is less number of interference, there is less interference and more isolation. Here you can see that in B figure, you can see that this is basically resource allocation, different two particular resource allocation for a given conditions for two base station and two slices. But in B figure, you can see that in the same PIB, we are serving the same slice. For a cell edge user, this means there is a more SINR compared to the C diagram. Here you can see it is being served at same PRB is served by two different slices. So it will cause interference, reducing the SINR. So in the existing method that we currently have, indifferences of base stations are modeled as binary. Say, for example, here base station 4 and base station 3 have some common overlapping cell coverage area. So in such cell coverage area, we say that there is interference. But rather than modeling it as how much like fractionalizing the indifference, what we have in existing method is either 0 or 1. And in the existing method, we doesn't consider the channel conditions or where the users are located. The only thing that we try to do is maximize the number of linked PRBs. So the motivation in our project is to bring out the channel conditions and try to maximize the rate rather than maximizing the linked PRB. So this is basically a problem statement. So basically a problem statement has both resource and power allocation to it. So how will you allocate resources and power such that the total sub-rate is increased, saying that only one resource you can put in one PRB. Only slicing profile has to be met, and the total power is restricted by the total transmit power of a base station. And the resource allocation indicator is a binary value, and power is a non-negative value. So this is a non-convex mixed integer problem. So in order to solve this, there is a suboptimal way of solving it. First is that we split the whole problem statement into two. One is a resource allocation problem, and another one is a power allocation problem. So in the first resource allocation problem, what we do is say there is an equal power is being distributed to all PRBs. How will you allocate resources? By keeping the power fixed. And when you get the resource allocation, now you say that given the resource allocation, how will you allocate the power such that the rate is being maximized? So this is the resource problem formulation, and this will be the power problem formulation. So in both the resource allocation and the power allocation, if we see that both are in the standard difference of concave functions structure. So a difference of concave function is basically you can write the objective function as difference of two concave functions, and the constraints are concave. It says in such a condition, you can use a standard difference of concave algorithm to solve the problem. So both in both resource allocation and in power allocation, we will be using the same. And by simulation, we can see that even in the resource allocation, it you can easily round it off to zeros and ones. And using the same allocation, DC algorithm, you can still use the power allocation, do the power allocation to maximize the sum rate. So by doing this algorithm, we can say that the total sum rate has been maximized. And also not only that, there is a large number of increase in the linked PARBs compared to the existing methods. And on top of it, considering novelty, we have also done the power allocation, which has never been done before, along with the resource allocation to maximize the sum rate. That's all about my project. Thank you.